That's another thing, isn't it? I would caution you, don't think about the discrete metric if you want to have a good intuition for metric spaces, okay? All right. So those are a couple big points. Theorem 1.6 is he says, let Y be a subspace of the metric space X. Then a subset U of Y is open in Y if and only if U is the intersection of Y with some open subset, V of X. That's hard to listen to. So Y, subset of X, and U, a subset of Y, all right? Then U is open in Y if and only if there exists open V, subset of X, such that U is equal to V intersect with Y, which is theorem 1.6. So X is a metric space. Fun fact, any subset of a metric space is itself a metric space. Sam wants me to say non-empty, maybe, I don't know. Huh.
I was thinking about making a snarky comment about how if you take a subspace,
So at least the start of class in here will be peaceful. So, no. Anyway, so let's see here. Maybe I should draw a picture of this. All right. So let's think somewhat geometrically, 3 dimensions. All right. And we could let the Y actually be like a puddle in the XY plane. All right. So what this theorem says is, if you want a set to be open, well, maybe I'm missing something here. Sorry, I feel like I missed something. He says the metric d prime from y cross y to r is the restriction to y cross y of the metric d. Yeah, okay. That's fine. All right, so, yeah. So the proof goes along the lines of, on y, you have d prime, which goes y cross y to the usual thing, where the distance, between 2 points, say p and q and y, is just the distance from p to q. All right, so it's just the distance where d is the distance function at x. So you're just restricting the distance function to the, right? Now, so if we're thinking of Euclidean distance in R3, if you think about the 3-dimensional distance function and you restrict it to like a puddle in the xy plane, well, it just becomes the 2-dimensional distance function in the puddle, right? You're just suppressing one of the, yeah. So that would be an application of this idea. But the larger, let me maybe draw a picture here. U is open. So maybe U is, something like that. I'll focus on an open ball in the puddle, but it could be an open square or something. But then, anyway, the point is that's the U. What's the V then? It's what? Right. You could just take the sphere, take a sphere. The sphere would be the V, so to speak. So like V intersect Y would give you the U. I mean, the details are in the book. I don't want to go through them. I'm really just more interested in presenting this idea to you, that if we restrict a metric to a subset of a metric space, and then we ask what are the open sets in a subset of a given metric space, the answer is that every set which is open in the subspace can be viewed as arising from the intersection of the whole subset and an open set in the superspace, which is containing it. This is actually a foreshadowing of the definition of subspace topology. We'll actually use this to define in a topological space, a subset of a topological space is itself a topological space where the open sets are precisely those that are formed by intersection of the whole subspace with the open sets in the superspace. This becomes a definition of the subspace topology in the next chapter. All right. I think it's more useful for me to say that than to show you the proof. So, and also I'm tired. So, next up here. Let me stop looking at the trees and look at the forest here for just a second. Goodness gracious. I am going slow. Sadness. I'm like 20% into the stuff I've studied for this class at the moment. That is not cool. I'm just going to keep going through, though. It is what it is, and sorry, guys. X in X, I need to pick up the pace in here somehow. X in X is adherent to Y. If for all r greater than 0, the ball centered at X of radius r intersect with Y is non-empty. All right. And then with this, we define the closure of Y. What is the closure of Y? It is denoted by Y upper bar. It is all points in X which are adherent to Y. Which, in other words, it means all points in X which are kind of stuck to Y, right? Like adhesive. Yeah. So he points out by properties of, well, anyway, you guys tell me, why is Y a subset of the closure? Right, if we pick any point in Y and we pick any positive radius, the center of the ball centered at Y is in, yeah, right? So this is for free. This is true for arbitrary sets. A set is always a subset of its closure, just like we saw that the interior is always a subset of a given set, right? But the reverse inclusion is not for free. If y is equal to y closure, if y is equal to its closure, then y is closed. It's a closed set. All right. He points out that the empty set is closed, and also the entire space X is also a closed set. By the way, the entire space is also an open set. Why? Yeah, we proved that we wrote the entire space as a union of open balls, right? So a union of open sets is open, so the entire space is open. But yeah, every point's interior. I mean, however, there's a billion different ways to show that. But all right, I am going to. Oh, I can't. I was thinking of doing some projecting, but that would require getting my computer, and by the time that all happens, it would have been a waste of time. All right. Let's see here. So I think at this point, I should just read for you some of the results in this section and sort of skip ahead a little bit, all right? So here we go. He says, intuitively speaking, a subset is closed if it contains all of its boundary points, all right? We haven't defined boundary point carefully at this point, but a boundary point would be a point where any open ball around the point contains both inside and outside the set. What is outside the set? Well, it's not a sub. I mean, yeah. Thank you. I forgot. It's like, how do you define outside a set? Not an element of. Like, that is actually, I'm very grateful for that because that is the definition and I should be able to say it. Goodness. All right, moving on. So theorem 1.7, if y is a subset of a metric space X, then the closure is closed. Very good. And the details are right here. They're quite explicit. Theorem 1.8, a subset Y of a metric space is closed if and only if the complement of Y is open. Okay, that ends up being the definition of closed in the topological case. Like we'll later define a set to be closed in the topological sense if its complement is an open set. So this foreshadows that, theorem 1.8. And he has the proof there. Theorem 1.9, the intersection of any family of closed sets is closed. But the union of any finite family of closed sets is closed. So the table's turned with closed sets. All right? And the proof of that, you just use De Morgan's laws with the theorems we already proved today, because an arbitrary union can be turned into an arbitrary intersection under the complement. And vice versa, for a finite intersection becomes a finite union when you feed it through the complement. So when you have the closed set is set is closed if its complement is open. That allows us to do the finite and arbitrary thing we did, like to transfer over to the closed case. It's just De Morgan's laws, which you could prove with Venn diagrams. All right, it's here. Next up, he defines a sequence. All right? He says a sequence in a metric space converges to X if the limit, this I probably should write. we write, in this case, xn goes to x, all right? Or the limit as n goes to infinity of xn equals x. Now, you're like, that's not a definition because we didn't define limit as n goes to infinity, right? So here he's assuming that you know the definition from calculus 2. Because what is d of xn comma x? That's a sequence of real numbers, right? So what this means is that for each epsilon greater than 0, there exists n in the natural numbers, right? Such that whenever n is greater than or equal to n, that implies that the absolute value of the distance, xn x minus 0, is less than epsilon. In other words, the usual definition of convergent sequence from calculus 2. Maybe the calculus 2 of yesteryear. I don't know if it's the calculus 2 of this year. They may be very rowdy by the time I get to this. I'm not sure they'll allow me this definition in class. I don't know. I'm going to try. I'll try. But anyway, my point is he doesn't have that in here because he assumes you already know how to take the limit of a real valued sequence. Okay? This is something you will, I'm sure, discuss in real analysis. Yeah. Lemma, the limit of a convergent sequence in a metric space is unique. The limit of a convergent sequence in a metric space is unique. So if we had xn goes to x and xn goes to y, right? Then x equals to y. How do we prove that? At this point in the lecture, if I'm going to prove something, it's got to be really easy. So, the distance from x to y is equal to what? Well, it's less than or equal to what? Yeah? Oh. How about xn? Yeah? But we're assuming that both of those go to 0, right? So as n goes to infinity, this goes to 0, that goes to 0, which shows you that we can make this arbitrarily small, which is to say that the distance from x to y is equal to 0, which of course is to say by the definition of a metric that x is equal to y, by the indiscernibility, right? So in a metric space, the convergent, two convergent sequences must converge to the same point. If you look at arbitrary topological spaces, we lose this. You can have convergent sequences. How's it go? I think, well, anyway, let me not get into that's the part of the course I shouldn't even start to teach. So, all right. Now, Theorem 1.11, it says let y be a subset of the metric space X, then X is adherent to X and X is adherent to Y if and only if there is a sequence in Y that converges to X. Y subset of X and X an element of X is adherent to Y, which is another way of saying what? X is an element of the closure, right? if and only if there exists a sequence, let's say y sub n, subset of y, yeah? Such that yn goes to x. So we could think about the closure in terms of sequences, right? We could think the closure of y is what? It's the set of all like limit points for convergent sequences in y. I think those are called accumulation points. But I should be careful. These words are used with precision and specificity in your real analysis course. Be careful to pay attention to how they're defined there. We have reached section 2. Section 2 is on completeness. All right? So I think I'll just say a few words here. So he defines a Cauchy sequence. All right? What's a Cauchy sequence? His definition of Cauchy sequence is a little different than I've seen before. I found it to be kind of cute. I mean, it's as you know, this is one of the things about Gamelin. He often finds a way of writing definitions in a kind of more calculational style than many authors. In other words, he finds a way of writing the definition in a slightly heuristic way, which really captures the calculational essence of the definition. And so he says a Cauchy sequence is one if xn is a Cauchy sequence if the limit as m and n both go to infinity equals to 0, yeah. That is not how I typically define it, all right? But that is a good explanation. What it's saying is that points in the sequence get arbitrarily close as you go on out far enough. Lemma 2.1, a convergent sequence is a Cauchy sequence. So so convergent implies Cauchy. The proof is simple enough that I will write it here. The distance from xn to xm is less than or equal to the distance from xn to x plus the distance from x to xm, right? And if we're assuming it's convergent, yes, sir? Sure. He doesn't say. But yeah, I think, I mean, nested limit is where I would start. I would say it means that for every epsilon greater than 0, there exists an m and an n, such big M and big N, such that whenever both big M is bigger than big M and N is bigger than big N, it follows that the absolute value of the distance from xn, xm minus 0 is less than epsilon. Yeah, I think so. Now, if we're assuming convergent, this goes to 0, that goes to 0, right? Hence, this can be made arbitrarily small, which is to prove that it's Cauchy. Do not give this proof in your real analysis course. It will not be accepted. I wouldn't accept it in real analysis. But there's a good heuristic proof. Convergent implies Cauchy. Now, the other direction, well, he has lemma 2.2. He says if xn is a Cauchy sequence, and if there's a subsequence, x sub nk of xn, that converges to x, then xn converges to x. So if you have a Cauchy sequence, and you can take a subsequence of a Cauchy sequence which converges to x, it will then follow that that subsequence drags the rest of the sequence with it to converge to x. So Cauchy is a pretty strong condition. It says that like convergence of a subsequence of a Cauchy sequence suffices to get convergence of the whole sequence. That's kind of a neat a neat condition. Definition, and this is really the biggest and most important definition in this section. X, a metric space. A metric space X, fine. Oh. Is complete. All right, it's complete if every Cauchy sequence in X converges. In other words, Cauchy implies convergent in a complete metric space. What are examples of complete metric spaces? What's that? The reals, right, good example. How about the rationals? Rational numbers. Take the decimal expansion of the square root of 2. Each one of those is a rational number, right? But the limit of that sequence is the square root of 2, which you have proved in Math 200 at least once is irrational. So the limit point is outside of the space, which means that that is not a convergent sequence, and yet it's Cauchy. Because you can prove that actually, the thing that's missing from this discussion is the proof that the decimal expansion, taking subsequent decimals in the expansion of the square root of 2 is actually giving you a Cauchy sequence in the rational numbers, but that can be proved. Yeah? All finite sets are complete? Yeah. I suppose that's true. He had a good example in here, which was not so out there as, rational numbers, that's a really greedy example, kind of technical example. Important, but, he had a really nice example. Just the open interval from 0 to 1 is not complete, because you can take a sequence which, is Cauchy because it's, right, it's a Cauchy sequence, but it's converging to a point outside the set. Something like that. You can exploit that. So I'll read you the major theorems in here. A closed subspace of a complete metric space is complete. And also, a complete subspace of a metric space X is closed. So complete subspace implies closed. And here's a theorem. Let S be a set, X be a complete metric space. Take a sequence of functions, which is Cauchy sequence of functions from S to X. Then there exists a function f from S to X such that Fn converges uniformly to F. And we'll come back and talk about that another day. I don't have time to. We'll talk about uniform convergence of functions some other time, okay, guys? And then he has for us here the bare category theorem. A sequence of dense open subsets of a metric space. If you have a sequence of dense open subsets of metric space, then the countable intersection of those is dense in X. Of course, you might wonder what does it mean for a set to be dense? What does it mean for a subset of a metric space X to be dense in X? Rationals are dense in the reals, because the closure of the rationals is the whole reals, right? So if the closure of a set is the whole set, then that's a dense subset. Yeah. It does seem like it's connected to the idea that if you take a open ball around a point, you're going to find something in that dense subset. Yeah, but that's not the definition that's given here. And then finally here, corollary 2.7, let En be a sequence of nowhere dense subsets of a complete metric space, then the union of these nowhere dense subsets has an empty interior. So I don't know, I think this section is interesting. I'd encourage you to read it, but I do need to kind of move along, so I'm probably going to go and start. Actually, let me just kind of, if you'll forgive me here for a minute. Next section's on the real line, and basically what's said in there is just a description of what is it that makes the real numbers the real numbers. It's that they're a complete ordered field. They obey that least upper bound property I told you about earlier. In fact, and here it is, the real line with usual metrics, a complete metric space. The next section is on products of metric spaces. And basically what this section says is, I've already covered part of this. It's got the circle in the diamond. So in particular, R2 is R cross R, right? So my examples 2, 3, 4, those can also be looked at in terms of just taking either the different norms on different. You can look at those in terms of products as well. But anyway, basically what this section says is just that if you have a Cartesian product of metric spaces, guess what? You can make it into a metric space. And it describes, and of course it assumes a couple of small conditions in this section. Like you have to, for example, you have to have, and if you took advanced calculus with me, you'll remember this. One of the conditions that we have to have on the metric is that the kth distance function from xk to yk has to be less than or equal to the distance from x to y. So x and y are like vectors. And we're talking about the kth component. So it says that the distance between a given kth component of a pair of vectors has to be smaller than the distance between like the whole vectors. We needed this condition on a basis for certain proofs about norm spaces, like that a component of a vector has to be smaller than the length of the whole vector. That would correspond to, say, the distance to the end of the vector has to be less than the distance of any like component of it, if you just put it from the origin. But that's more or less all that section says. The next section, 5, is on compactness, and that deserves our attention. So I'm going to start at compactness next time, and hopefully if I play my cards right, we should get through compactness and continuous next class if I do well, maybe further. I'd really like to wrap up metric spaces by next week. So, yeah. Anyway, thank you for your patience. And thanks for taking this course, by the way. I think this is a really exciting opportunity. There's not often this many people interested, and so it's good. And if we can really get a decent discussion of the measure theory at the end, I think it's really healthy for you guys in terms of going forward. So, anyway, I shut up. Yeah, you can turn off. Thanks, King.